case you haven't looked at your list of attendees, I want to let you know that with the possible exception of 1926, we have at least one person here from every single class since 1923. I think that's truly remarkable, and I want to congratulate you all. We have a very full schedule this morning, so I want to get off to a rapid start. And we'll begin with opening remarks by John Deutch, who's Provost of the Institute. John's professional career has been primarily associated with the Department of Chemistry and other endeavors, but the reality is he started things off with a bachelor's degree from our department, and I think his heart is still there. John?
Thank you very much, Mark. Well, I consider it a great privilege to have the opportunity to open this conference on behalf of the Institute. It's a privilege to participate in this Centennial celebration. And I'm pleased that I've been allocated a few minutes, just 2 or 3, beyond the normal cameo appearance expected of a provost, to actually share some thoughts about this Centennial celebration. This department has made remarkable contributions to the nation, to the economy of this nation, both in peacetime and in wartime. My own personal earliest recollections are of my father, who was an engineer, talking with Ed Gilliland and with Bradley Dewey about the problems of synthetic rubber in the Second World War in the early 40s and mid-40s. From that period, before that period to the present time, this department has been important to the country. It has also been exceptionally important to the Institute. And finally, it really has been exceptionally important to me personally. The faculty in this department had a very pronounced effect on my education and the way I think, and I'm, of course, like very many other people in this audience, extraordinarily grateful for that. Well, with this century of accomplishment behind it, and there has been just an enormous number of people who have made great contributions to the department to permit that century of accomplishment. I note the most recent contributions of Jimmy Way to leadership of the department, to strengthening it and making it an even more important unit at MIT. It is very appropriate to think about the challenges of the future. It's perhaps even especially important because I believe, along with many others, and I know you'll be hearing from Ralph Landau about this later today, that this nation really does face some very significant problems with respect to its science and technology activities and with respect to its record in economic productivity. And it is extremely, seems to be pertinent and correct that under such circumstances where the nation does face, I will use the word crisis, in its economic affairs, in terms of its long-term industrial productivity and economic competitiveness, it seems to me entirely appropriate that this department, which has done so much, raises its head and says, which directions should we continue to go in pursuing that record of accomplishments. It is also a subject, what we should do for the nation, for the nation's economy, more generally for the world, that is being broadly discussed within the MIT School of Engineering, and indeed throughout the Institute. And in that regard also it's appropriate for this department to look at the challenges ahead. I would like to just mention to you 5 questions that I think are important to keep in mind as one thinks about the next century of chemical engineering at MIT and in the country. The first of these questions has to do with the role of chemical engineering in manufacturing and in process industries. My judgment, chemical engineering, in contrast to many of the other engineering disciplines, has a much more impressive record of performance and its ability to deal with the practicing industry and with especially manufacturing and processing within the practical chemical industry. But we do have to consider, it seems to me, again, how we are going to deal with that in our educational curriculum here at the Institute. And I would be so bold as to suggest that the approach which is used in this Department of Chemical Engineering, including its practice school history, might be used as a model for other areas of engineering as well. Secondly, I believe that we have important number of new technologies emerging in this nation, well known to all of you here today. I speak especially of biotechnology, microelectronics, materials processing. These are new areas compared to the historical subjects of petrochemicals and plastics, if you like, of chemical engineering. And I think it is very important that we worry as chemical engineers how our educational efforts will be designed to make the contributions to these new areas, biotechnology and microelectronics, materials, that it did to its historical areas in the past. Third, I am struck, because of some of my own personal background, about some of the importance to industry of international questions of energy availability, of questions of environmental impact. And I think that we still have some very major questions about how these issues, the international context of business, energy, and the environment, should be integrated into the considerations of the chemical engineering education, both at the graduate and undergraduate level. Finally, I am interested especially because, as mentioned, I am a chemistry professor, not a chemical engineering professor, the interaction between chemical engineering and the fundamental sciences. It's a very important subject. How do we introduce chemical engineers to the fundamentals of chemistry, physics, and of course now, in a much more important and interesting way, modern biology? These are all important questions that I hope will be dealt with in our thoughts and perhaps even in the comments during this convocation. As I say, all of this is to be accomplished in the next century, these exciting challenges, while maintaining excellence and while maintaining a central focus of the discipline. We have an enormous diversity, a welcome diversity within the practice of chemical engineering and its scholarly attributes. In my judgment, it has been one of the really magnificent accomplishments of the intellectual world of the United States, of science and technology in the past century, and I'm confident that it will be so during the next century as well. Thank you very much.
Our next speaker, known to his colleagues as Skip Scriven, is a distinguished scholar from the University of Minnesota, and this year he was the Warren K. Lewis Lecturer in the department. Just a few days ago, we were treated to a marvelous lecture on his recent research, which I think in the future will be looked back at as a landmark in the development of chemical engineering. Today, however, he himself is going to look back and tell us about his views of the early intellectual development of our discipline.
Good morning. I want to report that I've been a student of chemical engineering at the Massachusetts Institute of Technology since I was an undergraduate in Berkeley and nearby Shell Development, and a much more acute student since joining the department's visiting committee some 9 years ago. That adds to my pleasure in participating in this convocation and sharing with you some views of our discipline's early evolution. The announced title, modified just now by Clark, I notice, but what you see printed is not fully accurate, but the best that he and I could come up with some months ago. I should add that we'd planned to collaborate in this endeavor until he was overtaken by the planning for not only this convocation, but also the marvelous academic symposium hosted by the faculty these past 2 days. But Clark did find a few hours now and again to be my sounding board, and I want to express my appreciation of those very stimulating sessions. My first point this morning is a reminder that chemical technologies are dynamic, as are all others. Their rates of evolution wax and wane, but there is a pattern. May I have the first slide, please? My diagram derives from one by William Abernathy and Philip Townsend, an electrical engineer and an economist chemical engineer, both turned doctors of business administration, in their 1975 article in Technology, Productivity, on Technology, Productivity, and Process Change, in which they analyzed what they called the life cycle of a technology or industry, but which seems to me a pattern of evolution. Successive processing technologies spring variously from scientific discovery and technological invention. They're developed and commercialized, which many call innovation. That is, they rise, they flourish, and they diffuse to other owners and to other nations, gaining broader application, engendering greater competition and lessened profitability. Then they subside into the industrial background of mature technologies, or they may be displaced by newly emerging processes or products. Some persist, perhaps metamorphosed, some disappear, but all evolve. Slide off, please. The first chemical manufacturers to be innovated in the modern sense were the chamber process for sulfuric acid in the mid-18th century in England and the Leblanc process for sodium carbonate, which originated in France around the turn of that century and soon diffused to England and throughout the continent. Both stimulated other technological developments, some stemming from what would today be called their environmental impacts. Both drew competition, the one from vapor phase catalytic processes for sulfuric acid, but not until those were commercialized some 50 or 60 years later, which finally replaced the chamber process in the early 20th century by and large. The other from the marvelously inventive Solvay process, which more rapidly replaced the early Leblanc technology. Both of these newer technologies, heavily metamorphosed, are in the industrial background today. Chemical engineers at large pay them little heed, though annual U.S. production of sodium carbonate is about 10 million tons, divided between the Solvay process, still, and mining at Trona. Sulfuric acid is, of course, an equally basic commodity chemical. Solvay's 1872 ammonia soda process was a breakthrough. He broke it up into separate operations of gas-liquid contacting, reaction with cooling, and separations. He invented new types of equipment for carrying them all out continuously on a large scale. And he himself dealt with the chemistry, the materials handling, the process engineering, and the equipment design. In short, he performed as what would come to be called a chemical engineer. Though that was not evident to his contemporaries, it surely impressed the aggressive Americans who soon licensed the process and integrated it into a fast-developing inorganic chemicals industry that would be invading European markets around the turn of the century, 1900. In these two heavy chemical lines are the roots of chemical engineering. They brought the need for chemists and engineers in chemical manufacture. They also gave rise to George Davis, English industrial entrepreneur who in 1880 turned Environmental Protection Act enforcer, hydrochloric acid contamination of the British Midlands countryside. By 1882, he was calling publicly for chemical engineering and a society to institutionalize it. The society, which he helped to found, chose instead to be called the Society of Chemical Industry. Then in 1887, George Davis became some sort of adjunct professor in Manchester and gave a course of published lectures on his new subject. And finally, in 1901, he turned these into the first book on the discipline of chemical engineering. I have the slide, second slide, please. His preface highlighted the mounting competition from America in heavy chemicals. This is the Britisher writing. And, as he put it, the wonderful developments in Germany of commercial organic chemistry. An expanded two-volume second edition was published in 1904, and it is pictured here. You see the radical departure from the earlier textbooks and handbooks on industrial chemistry, which covered each chemical industry separately. Davis had recognized that the basic problems were engineering problems, and that the principles for dealing with them could be organized around basic operations common to many. Fluid flow, if you look closely, solids treating, heat or cold transfer, extraction, absorption, distillation, and so on. As W.K. Lewis noted much later, the concept was developed here in this book as quantitatively as the resources of the 1880s had allowed, not very quantitatively. Unfortunately, very few people were ready to act on George Davis's vision of a discipline of chemical engineering, either in 1887 or in 1901. It fit no university curriculum of that time, but it did not go unnoticed in the United States, where there were those who called themselves chemical engineers, and a university curriculum called chemical engineering. May I have that slide off, please? The next chemical manufacturers to be innovated were batch processes for small volume production, high value added dyes and other coal tar derivatives, beginning with Perkins mauve or indigo in England, but very soon dominated by German research prowess in organic chemistry and its successful integration into an industrial juggernaut that soon controlled international markets. Early pharmaceuticals followed the same route. Here, though, the research chemist's laboratory methods were turned over to a mechanical engineer to scale up directly. There was no harbinger of chemical engineering, nor did it lead the way to continuous processing and the economies that could bring when markets expanded and competition demanded. Meanwhile, the sugar industries, sugar beet and sugar cane, distillation industries, and many others were evolving in Europe. Process engineering and industrial chemistry curricula were being installed in the new technical universities, the Technische Hochschule, that had appeared in Germany, Switzerland, Austria, and even Hungary. A few of the professors and their counterparts, chief engineers in certain companies, highly educated in science and mathematics, took to analyzing common constituent operations like heat transfer by Peclet in France, vaporization, condensation, and drying by Hausbrandt in Germany, distillation by Hausbrandt and by Sorel in France. Monographs on all of these subjects were published by these authors between 1880 and 1899. These, too, were important forerunners of chemical engineering. Electrochemical processing rose in England, Germany, and France in the decades before 1900, but it diffused to America, where cheap electricity, generated from cheap coal at first, and mass production in the new tradition of iron, steel, copper, nickel, and tin enabled the Americans to compete successfully, even invading international markets, for example, with electrolytic caustic soda and chlorine, two of the items that bothered George Davis in that preface he wrote. In the United States, Charles Hall invented in 1886 the most successful process for producing aluminum, and there were many other such developments. In 1895 came the hydroelectric development at Niagara Falls, and by 1910 that was the location of, and I quote, the world's greatest center of electrochemical activity, and not only of production, but also of process research and product development. Outstanding was Frederick Beckett and his Niagara Research Laboratories, where he invented processes for making carbon-free chromium, tungsten, molybdenum, and vanadium by direct reduction of their oxides, and other important processes as well. This was one of the very first industrial research labs in America, and it and Beckett were soon bought up by the Union Carbide to be theirs. There's something else about Beckett. He was educated as an electrical engineer. When he got into the electrochemical processing area, he went back to school at Columbia University to get physical chemistry and industrial chemistry. He earned an MS in 1899 and all but completed a PhD in electrochemistry in 1902, several years before he went to Niagara. Electrochemistry at that time was the glamour science and the emerging technology. The Electrochemical Society was the meeting ground for leaders of the new science of physical chemistry, like Ostwald, Nernst, Bancroft of Cornell, Whitney, who moved from MIT to Schenectady to head General Electric's brand new research laboratory, the country's first corporate research establishment. The Society was the meeting ground for the leading electrical and electrochemical engineers like Steinmetz of GE, Tesla of the Independent, Burgess of University of Wisconsin, and Burgess Battery, for educated inventor entrepreneurs like Elmer Sperry, then of National Battery, later of gyroscope fame, and Herbert Dow of Midland, and for prominent industrial chemists and chemical engineers like Samuel Sadler of Philadelphia, William Walker of the Partnership of Little and Walker in Boston, and Fritz Haber of the Karlsruhe Technical University in Germany. As a matter of fact, all of these, save Sperry, Dow, and Sattler, presented papers at the semi-annual meetings of the newly formed American Electrochemical Society in 1902, 1903, and 1904. With the mention of William Walker, let's go back to the 1880s and the scene then in America's colleges and universities. Industrialization of the country was accelerating, and with it the need for engineers and, to a lesser extent, chemists. From decades earlier, there was popular demand for relevant college education, and this had been answered by the appearance of engineering schools like Rensselaer, first of all, Brooklyn Polytechnic, and MIT. Also scientific schools at Yale, Harvard, Dartmouth, Columbia, and so on. And, more importantly, I think, by the Morrill Act of 1862, which enabled the states to establish land-grant colleges. By the 1880s, there were strong curricula in science and engineering that had sprung up in many of these, among them the Pennsylvania State College. There, young William Walker enrolled in 1886 and graduated in chemistry in 1890. Having been a good student, he set off for graduate study in Germany, as did some 1,000 other top graduates in chemistry between 1850 and World War I, and perhaps 9,000 more in other fields. Germany was then the center of freedom of learning, freedom of teaching, academic research, and chemistry. Returning from Göttingen with a PhD in 1892, Walker taught a couple years at Penn State, moved to MIT, then resigned in 1900 to join MIT chemistry graduate Arthur Little in a consulting industrial chemistry partnership. Little, by the way, had lost his original partner, Griffin, in a laboratory explosion. At MIT, as at many other schools, individual courses and laboratories in industrial chemistry, largely descriptions of the manufacture of diverse chemicals, were being taught in the 1880s. The teacher at MIT was Louis Norton, an MIT graduate and an 1879 Göttingen PhD in chemistry. He'd been a textile mill chemist several years and had come to appreciate engineering problems of not only, and I quote him, the textile industry, but also of furnace construction and regulation and of the manufacture of organic products. Impelled, he wrote, by a demand for engineers skilled in chemistry, in 1888 he proposed a new curriculum, Course 10, to be mainly the mechanical engineering curriculum, but with industrial chemistry courses and laboratory in the third year. Norton lined up Professor Peabody to teach a special course on, and again I quote, chemical machinery from an engineering point of view, pumps, refrigerating machinery, filter presses, and methods for evaporation in vacuo. And Norton himself began developing a companion fourth-year course he called Applied Chemistry. The name Norton chose for the new curriculum, 1888, was chemical engineering, though the curriculum itself contained no course called chemical engineering, and it was taught by no one called a chemical engineer. The proposal was approved by the faculty and by the corporation. 11 sophomores were dragooned or somehow enrolled in the new curriculum, and they embarked on it exactly 100 years ago. And so here we are today. Louis Norton died less than 2 years later, at age 38, I think it was, and the curriculum reverted to mechanical engineering plus industrial chemistry, the combination that began to be called chemical engineering elsewhere, the University of Pennsylvania being next in 1892. So begins an acorn to grow, Arthur Little may later have said. May I have the next slide, please? Coming back to 1902, in that year, William Walker not only became a charter member of the American Electrochemical Society, he also accepted an appointment in the chemistry department at MIT to head Course 10, though he continued his partnership with Arthur Little until 1905. To his new position, he brought his recollections of Norton's ideas, his own annotated copy of George Davis's book on chemical engineering, and principles he had in mind for transforming the chemical engineering curriculum. From what happened, it's plain that his program was to incorporate the new sciences of physical chemistry and thermodynamics, the new engineering sciences, we would say today, of heat transfer, distillation, evaporation, and fluid mechanics that had emerged in Europe, to organize a chemical engineering course including laboratories around Davis's conception of what would come to be known as the unit operations, and also to develop research through student theses and industrial interactions. May I have the next slide, please? The success of Walker's program was assured when he arranged for a 1905 graduate, Warren Lewis, to go to Germany for a PhD in chemistry at Breslau. For upon returning in 1908, Lewis joined in and embarked on a series of published analyses of distillation, filtration, fluid flow, countercurrent contacting, heat transfer, and so on, most of them involving bachelor's and master's theses. These researches developed principles of chemical engineering, which were expounded in mimeograph notes for classes, and then the famous 1923 book by Walker Lewis and the younger McAdams, who had joined them in 1919. The first textbook, and a fine one, and of course shaped the discipline and helped define the profession. May I have the next slide, please? Walker's program was further reinforced by his former partner, Arthur D. Little. In 1908, they took part in a meeting in Philadelphia to organize an American Institute of Chemical Engineers against the decided opposition of the American Chemical Society. Incidentally, it appears that no one with a degree in chemical engineering was among the industrial chemists and mechanical engineers who founded the AICHE. Walker himself delayed joining until well after he'd been president of the Electrochemical Society in 1911. Little until after he'd been twice president of the ACS, 1913, 1914. Anyway, from 1908, Little took increasing interest in chemical engineering education, by 1915 as chairman of a visiting committee. In that year's report, Little recommended establishing a school of chemical engineering practice, which was duly started the next year with George Eastman's endowment. I think it was $300,000. In the same 1915 report, Little, famous as a fine speaker and writer, particularly on the need for industrial research in America, coined a name that stuck. It was unit operations, for those basic physical operations in chemical manufacture that Davis had written about decades earlier. What none of them got around to identifying, Davis, Walker Lewis, or Little, were the basic kinds of chemical operations in chemical manufacture. But there's not time for that story. Nor is there for the story of how Little led the later stages of the AICHE's 12-year effort, which ultimately succeeded, to define chemical engineering, prescribe the basic curriculum, and establish a national accrediting scheme, the first in engineering. I have the slide off, please. The transformation Walker and his associates worked at MIT was abundantly successful, though not without stress and strain, over chemistry and chemical engineering in one and the same department, and over the role of contract research in a university. So it is, at any rate, that Walker is widely regarded as the father of the discipline, and MIT's department, which split from chemistry in 1920 and was headed by Warren Lewis as the center of early development. Testimony to the success were the impacts of its graduates, ideas, approaches, and research results on the chemical and petroleum industries of the United States, which had come out of World War I, the world's #1 economic power. In the decades before the war, Nernst and Haber and others in Germany had taken up gas phase reactions and were soon pursuing nitrogen fixation by ammonia synthesis, a goal of tremendous economic and geopolitical significance and recognized in other countries as well. Haber got the breakthrough by discovering a catalyst in 1908. Badische Aniline und Sodafabrik, BASF, took on the development, assigning to it a self-made chemical engineer, Karl Bosch. He was a mechanical engineering graduate of Leipzig University with a PhD in industrial chemistry. He worked with Alvin Mittasch, a chemist who oversaw 20,000 trials with different catalyst formulations to find the best. Bosch designed the first high-pressure continuous flow tubular reactor, actually a tube bundle, and the rest of the plant. In 1913, they had the Haber-Bosch process for synthetic ammonia in operation and patented, a signal accomplishment like Solvay's 50 years earlier. After the war, German technology was a war prize. And in America in the 1920s, process innovation turned to high pressure and often higher temperature processes, capitalizing on German advances in vapor phase catalytic reaction processes. The first products were synthetic methanol and other commercial solvents, setting the stage for the coming era of chemicals from petroleum feedstocks, now looked upon as the tradition in chemical engineering. The feedstocks were in particular the refinery off-gases, which were being burned as fuel, rising amounts of ethylene and other olefins among them. More and more petroleum was being thermally cracked to increase gasoline yield, and olefins were a byproduct. This large and expanding area of opportunity for chemical engineering was overshadowed by petroleum refining itself, which had developed out of the mainstream of chemical processing. Thermal cracking, a crude kind of reaction processing, had been innovated by Standard Oil in 1912. Catalytic cracking was a couple decades in the future. Distillation separations, incredible as it may seem today, were a batch process in refineries until, in the post-war years, continuous flow pipe stills and fractionators came in. Abruptly, there was a high demand for analysis and design of distillation equipment. May I have the next slide, please? Clark Robinson of MIT, who had graduated in 1909, spent 5 years in industry and returned to do a master's and join the staff, obliged in 1922 with the first physical chemistry-based text on the elements of fractional distillation. It was a bestseller, relatively speaking. What I find remarkable is that in the same year, Robinson also published a book on the recovery of volatile solvents, and the next year he co-authored a seminal little book, a seminal little textbook with Professor Hitchcock of the mathematics department. May I have the next slide, please? A remarkable outburst of book publication. Here's the little book, Differential Equations in Applied Chemistry. It's been unsung for years, though it went into a second edition in 1936. The preface acknowledges the goading of Warren Lewis in constructing the book. I highlight it because I recently learned that this little book, sitting in the library of a state university in the southern portion of the United States, was the inspiration of Bob Pigford, who became a prominent chemical engineer. How difficult it is to know when such events take place that set careers in motion. May I have that slide off, please? I'd like to skip the next two slides. I'll have to close off the story without getting into how unit operations research sprung up in other places, and the center of mass shifted by the late 20s to Tom Chilton's famous group of chemical engineers in DuPont's experimental station. But I shouldn't leave these views of early evolution with you without making a point. In the early 30s, one of Chilton's people from MIT, John Perry, led the construction of our Chemical Engineer's Handbook. It was a compilation of the best and the most useful of American chemical engineering. It happens that at the same time in Germany, Eucken, Jakob, and Haber were editing a multi-author, multi-volume German Handbuch der Chemie-Ingenieur. May I have the next slide, please? Here they are, Perry's handbook in front, the Handbuch lining the table in the back. You can count the number of volumes. My point is that although the discipline and the profession of chemical engineering had been born and grown up in the United States, still in the 30s there was a greater repository of expertise and knowledge, especially science-based knowledge, in the German chemical industry and universities. One can question why there was not more assimilation on this side of the Atlantic, of reactor design, for instance. Eucken, Jakob, and Haber, in the first volume, the first part of the first volume there, in their preface, acknowledge their great debt to the concepts of Walker, Lewis, and McAdams in the book of 10 years earlier. Let me sum this up with a view of the name changes of the magazine that started out. May I have the next slide, please? The magazine that started out Electrochemical Industry on the left in 1902. That's the year the Electrochemical Society was founded. It went through changes in electrochemical and metallurgical industry, metallurgical and chemical engineering, and by 1918, it was chemical and metallurgical engineering, and so it remained until 1946, when it became just chemical engineering. If you look very closely, there's something about metallurgical engineering under the masthead. May I have the slide off? In closing, I want to say that in my sporadic rummaging through the literature, nowhere have I found described what is surely an interesting subject, worthy of being developed by scholars of engineering and technology. What makes an engineering discipline like chemical engineering? And what maintains the associated profession? How does it depend on the industries served and the way their technologies evolve? and chemical technologies most certainly do go through life cycles. How does it depend on neighboring disciplines like chemistry, electrochemistry, metallurgy, and now material science and the competition amongst them? How does it depend on publication of textbooks, handbooks, professional journals, and research journals? How does it depend upon university curricula and accrediting bodies, on university department structure, on its relation to source science, like chemistry? How does it depend on the professional society or contending professional societies, as in the case of chemical engineering? And no doubt most important of all for an engineering discipline, how does it depend on the interaction of the universities and the industries served, the established ones, the emerging ones, the expiring ones, the intellectual interactions above all? Surely the question of what makes chemical engineering tick is interesting to chemical engineers, and when we know the answer, we ought to be able to steer the discipline toward its next centennial convocation. Thank you.
Thank you very much, Skip, for an extremely interesting presentation. Next, we have a bit of a treat, especially for some of our older alumni, because we're going to have two of our professors emeriti who were here in the 1920s at a time of great activity tell us their personal reflections on those early days. First, we'll hear from Professor Hottel, who entered the Institute just a year or two after the department was formed. Hoyt?
Skip, what you said makes me feel that what I have to say is unimportant. My thinking back to the early 20s when I decided to become a chemical engineer triggered such a flood of memories that my choice of what to cover was difficult. I have chosen the exciting decade of the 20s. That was the period in which MIT was at a low ebb, but finally started on a dramatic rise under Carl Compton. The period in which chemical engineering was outstanding among MIT's departments and set the pattern of high competence which it has maintained since then. The period that embraces Warren K. Lewis's headship, and a period about which I can speak mostly firsthand because I arrived here for graduate study in 1922. I shall describe engineering at MIT in the 20s, then four of the extraordinary chemical engineers responsible for that early picture. MIT's Department of Chemistry was so overloaded with students in the chemical engineering option by 1920 that chemical engineering, as Dr. Scriven has told you, was made a separate department that year. May I have the first slide, please? The first slide, please. There are many ways to measure department quality. The doctor's degree was not common among engineers in 1920, but the number of such degrees granted is one measure, perhaps not the best, of department leadership and change. This figure shows the growth of the doctorate program in MIT's engineering departments and the leadership of chemical engineering. In a 10-year period, 39 doctor's degrees in course 10 versus 3 or 4 for each of 5 other engineering departments. The science departments on the right were in large measure service departments for engineering students. Only chemistry was serious about the importance of the doctorate. Some measure of the contrast between chemical engineering and other departments at that time. In my student days, chemical engineers took a lab course in mechanical engineering involving primarily the testing of engines and pumps and taught on a recipe basis. We also took our thermo in the mechanical engineering department, taught by the department head, Professor Edward Miller. The only fluids were steam and air, no chemical reactions, and time was spent on diagrams showing how to fix the opening time of steam engine D-valves. But D-valves had stopped being built about a decade before that, D-valve engines. I remember one class in which, after instruction on isentropic expansion of steam in a cylinder, a student said, "Professor Miller, what is entropy?" Miller's reply, "Well, it's what you use to find the exit condition of your steam. If you go down this straight line," he never answered the question. Sometime in the 20s, our department decided to teach our own thermal, and we also replaced the engine lab course by a chem engineering lab. Other measures of low ebb. The head of civil engineering said in the 20s that the doctor's degree was a waste of time for engineers. The head of physics was a specialist in thermal conductivity of refractories. The only infrared spectrometer in the whole of MIT was one designed by me and built by a master's thesis student named Ravel to measure the radiation characteristics of fabric. It was later borrowed by Professor Harris in the chemistry department to study the structure of benzene. Today's chemistry and physics departments find my story hard to believe. Back to the good side of the 20s, the chemical engineering department nurtured ideas that affected other departments. I lost my place. The first of two SCD theses in chemical engineering, those of John Keats and Charlie Hertie, were on ferrous metallurgy. Lewis's contacts with Bethlehem Steel through our practice school station at Lackawanna made him think that George Waterhouse, an English metallurgist at the steel plant, could fill a blind spot in the metallurgy department. So Waterhouse was made a professor in metallurgy. Nuclear engineering started in chemical engineering, and when it became a separate department, we lost 4 men, all distinguished in their later careers. The Department of Food Technology for some years used Walker Lewis, McAdams, and Gilliland, with problems recast to fit the new kind of interest. Fuel and gas engineering was spawned by Haslam and Chemical Engineering in 1925 and went back into the department in 1932. I had been against its separation in the first place. On men, and now this is most of what I have to say. The chemical engineers in the chemistry department before 1920, before the 1920 split, included some very strong characters: outspoken, argumentative, able, self-confident, and I'll spend the rest of my time on 4 of them: Walker, Lewis, Wilson, and Haslam. May I have the next slide? I despair of evoking in you the reactions to these men of the chemical engineers who knew them in the 20s. Most of you relative old-timers knew only one of those 4, Lewis. But William H. Walker, was Lewis's idol, and that word is not an exaggeration. Walker had a PhD from Göttingen. He was head of the engineering option in chemistry from 1910 until he left MIT. Walker was poised, gentlemanly, absolute master of the English language, and strong in his convictions, so strong as to get himself in trouble. Lewis was a much better chemical engineer, but in the 20s he was, by comparison with Walker, an awkward country boy. He said so himself. But the two were alike in the high intensity of their reaction to life's stimuli. The growth of their mutual respect shows in a story about Lewis's early days as a research assistant. A student felt improperly that he'd been unfairly accused of cheating by young Lewis and went with his story to the department head, Dr. Talbot. Goatee-bearded, pompous Talbot called Walker in and asked for an explanation. Walker defended Lewis with his customary intensity and abruptness, saying, "The student hasn't a leg to stand on," and left. Then he went to Lewis and said, "Lewis, what the hell have you been up to now?" Walker founded the Research Laboratory of Applied Chemistry, or RLAC to all Course 10 men, in 1908, 5 years after the distinguished physical chemist Arthur Noyes founded the Research Lab of Physical Chemistry. Two very able men, each so strong in his views as to have near contempt for those of the other. Walker's own words, and I quote, "Science by itself produces a very badly deformed man who becomes rounded out to a useful creative being only with great difficulty." Noyes was equally disparaging in his comments on the value of teaching engineering. Both had excellent objectives, both went too far. But RLAC in the 20s was a great success, an important addition to chemical engineering teaching. To save time, I have to skip some of it. But it multiplied the friction between Noyes and Walker until each left MIT. Noyes in 1919 to California to help convert Throop College into Caltech. Walker in 1920 to go back into consulting work. Walker's large contributions to chemical engineering included his development with Little of the unit operations of chemical engineering concept, his contributions to the Course 10 Bible, Principles of Chemical Engineering. He insisted on clarity of expression and rewrote or demanded rewrite of significant parts of that book. The next slide, please. I could not find a picture of the man I want to focus on next, Wilson, with the red mark under him. But time doesn't let me talk about the others that you recognize. Mack on the left, the conscience of the department in telling an engineer what to bet on. Haslam, Lewis, Wilson, and Robbie, the man who wrote the textbook we heard about. And in the second row on the left is Walter Whitman, and on the extreme right, Dan Barnard. I don't know the others, but I knew those seven. When Walker left RLAC, Robert E. Wilson became director. Wilson had been a boyhood friend of Carl Compton, growing up in the same town. He had graduated from MIT in 1915 and had become a major in the Chemical Corps in World War I. Wilson was a fast thinker and hard driver. He doubled RLAC's industrial contracts, expanded its staff to over 30, and was responsible for many papers being published. He enjoyed arguing with Lewis. He noticed that Lewis had a technique of forming or of unearthing a technical statement that was true, but at first thought appeared wrong, and of presenting it bombastically to start an argument. So Wilson played the same game. In the spring, Lewis would receive a photostat copy of a page out of Wilson Internal Revenue Return, including such a statement as $3 received from W.K. Lewis on dollar-to-donut bets. In 1921, Wilson left MIT to become, at age 28, Director of Research of Standard Oil of Indiana. Robert T. Haslam followed Wilson as Director of RLAC. The next year, Walter Whitman became the Assistant Director under Haslam, and 2 years later followed Wilson into Standard Oil of Indiana. Whit told me this story about his two bosses. Shortly before Wilson left MIT, Lewis, Wilson, Haslam, and Whitman had lunch together at Walton's restaurant on Mass Avenue, where the Stratton Student Center now stands. As they walked back to Building 2, Wilson and Lewis in front, and Haslam and Whitman behind, Wilson suggested to Lewis that the issue by the department of a memorial volume of RLAC publications under Wilson's stewardship would be appropriate. Lewis managed to sidestep, and Wilson kept on, saying that RLAC would probably never publish as many papers in 1 year as it had during the past year under him. Whitman and Haslam were, of course, listening, and Haslam gritted his teeth and murmured to Whit, "The Research Laboratory of Applied Chemistry will publish more papers in this coming year than last if I have to copy them out of the Encyclopedia Britannica." The story measures both men. I had an enormous respect and warm feeling for the Wilson I got to know years later. He'd lost some of that egotism, I think, by then. We were together at a technical meeting at White Sulphur Springs, Virginia in 1935. Wilson was by then president of Standard Oil of Indiana. At the day's technical meeting, he vigorously joined in the discussion of papers, an activity similar to his well-known performance at ACS meetings. He had a national reputation for that. That evening, the two of us took a long walk together, and I said, "Dr. Wilson, I can't understand how you find time to run Standard of Indiana and come to these technical meetings and participate with such obvious enthusiasm." His reply, "Well, I have to have some way to relax." Wilson moved from presidency to chairman of the board and then became a member of the Atomic Energy Commission. As I've said, Haslam took over from Wilson. Haslam, after graduating from MIT in 1911, had taken a position with Union Carbon Company, and within a year, the man who had employed him was working under him. Having returned after World War I to MIT to head up the practice school, Haslam was happy to add direction of RLAC to his activities. I'm going to insert something here that's not part of my story. Next slide. The next slide, please. That's Tom Sherwood and me on a Sunday afternoon in South Brewer, Maine. 60-second exposure, and to stop it, I threw my cap over the camera lens. That's as much as I'll have time to give you on the practice school. Where am I? Haslam was happy to add direction of RLAC to his activities. He increased the size of the staff. The slide off, please. He published many papers, some of them positively not meriting publication, found time to write a book, Fuels and Their Combustion, with Russell, set up a course in fuel and gas engineering separate from chemical engineering, went with Russell to Germany to arrange cross-licensing of hydrogenation, called virginization, of heavy oil and brown coal between Standard Oil of New Jersey and E. Farben. And the U.S. in 1927 thought it was running out of oil. And in 1928, left MIT to become manager of Standard Oil Development Company, now Exxon Research and Engineering. He was senior vice president of the world's largest corporation, Standard Oil of New Jersey, when he retired, going into W.R. Grace. I've described 3 of the 4 strong characters that I mentioned earlier. The next slide, please. Lewis is left, a product of Walker, just as Haslam and Wilson were products of Lewis. Doc to all of us in Course 10. I disagreed with Doc on some points of principle and a few in the area of ethics, but I've known no one well who has stimulated me more or taught me to admire straight thinking and try to achieve it more, or whose sense of fairness, of true concern over the problems of society, politics, and conduct I consider to have been as well developed as Doc's. Discussions, almost sermons, were frequent, sometimes bombastic, but always impressively organized, and Doc's capacity to stretch a few facts, to reach valuable new conclusions, and his impressive memory sometimes shamed me. I once asked a question which showed ignorance of the basis for what seemed an ingenious technical argument. His reply, "Why, Hottel, don't you remember you showed me that several months ago?" The next slide, please. I'll have to skip 4 never told and I think rather good stories of Lewis to gain time to emphasize his capacity to teach how to think straight. Industrial stoichiometry was his best test vehicle, and he so sold me on it as a tool for teaching straight thinking that in my graduate class in combustion, I took the first 2 days of the term to review combustion stoke. But to show the new graduate students that reviewing undergraduate stoke was not an insult to them, I gave for several years a 10-minute written quiz at the very beginning of the first class of the term. But to answer that quiz, you who've been exposed to Lewis don't need pencil or paper or slide rule or calculator, and you don't need 10 minutes. You just need to look at the ceiling and think a la Lewis for 1 minute. Here it is. Methane is burned completely in a furnace, the stack gas of which analyzes 10.5% CO2 or set. What percent excess air has been used?